it's Mr. Jones, and I'm back with another learning video. Today we're going to talk about representing the operations of fractions. So as we have discussed in class, there are three levels or categories that we can access to complete our math work. These make up something called the CRA model, which is a teaching strategy or instructional strategy that teachers often use, but something we can think about when we're solving problems. So there are three categories. There's concrete, which would be like real, everyday, hands-on things. If you can manipulate it with your hands, then it's concrete. Representational, which is usually some type of image or drawing or diagram that represents something concrete. And then abstract. So these are symbols that represent representational or concrete things. But we could also use, numbers would be an example of that, but things like variables in algebraic expressions would also fall under that category, which would be very abstract because they represent unknown values. So here's that same model applied to the addition of fractions. So our concrete example, we have some fraction strips that you would find in most classes, and this is showing that when you add 1/4 plus 1/2, it's equal to 3/4. The representational version is basically the same thing, but it's a diagram or drawing of that same thing. And then when we have our abstract version, now we're using numbers, right? We're solving an expression. So I want to start off by talking about incorrect representations, because there are a lot of misconceptions when it comes to how we can represent fractions in general, and then how we can represent operations of fractions. So incorrect representations often occur when we either mix levels or categories, or when we misunderstand what a fraction is really telling us. So this is an example of mixing levels because we have a plus sign and an equal sign with our fraction strips. So the plus sign, the equal sign, they belong in the abstract realm, and it doesn't really make sense to include them with representations. As we saw in the previous slide, just having these side by side is a good way of expressing that addition sentence. Another example of mixing levels, this time it might even be worse, because what this person's trying to represent is 4/6. But you see that in total they actually have 10 counters here. They have 10 circles. So what this really looks like is 4/10, even though what that person means is a fraction with a 4 on the top, a 6 on the bottom, right? 4 in the numerator, 6 in the denominator. So this is an even worse example of mixing levels. So not only have they included the symbols from abstract sort of number-based math, but they've literally one-to-one taken the numbers and made that many counters, not realizing that that doesn't represent the fraction the way they think it does. So here's another example. This is an example of not understanding what a fraction is really showing. So here the person is trying to express 10/12, and they've said, okay, well, I'm going to use 3 sort of pizzas, 3 fraction circles, and altogether I have 12 pieces, which is my denominator, and I'll do dots on 10 of them to show that they're eaten up or they have pepperoni or something. But as I noted down here, this is actually showing 10/4. So with a fraction, it's not just how many fractional pieces it's divided up into, it has to reflect the number of wholes as well. So here we actually have 3 wholes that we're working from, whereas the fraction 10/12, it should be 1 whole that's divided into 12 pieces. So our first multiplication representation is the area model. So in this model, we use usually a rectangle, but it could really be any symmetrical shape when I think about it. And we sort of overlay 2 different fractions. So here I've divided A in half, and I've shaded orange 1/2 of that. So that's representing our 1/2. Here I've divided, going the other direction, I've divided it into fifths. And here I've added stars to 4/5. If I had the capability to, I would sort of cross-shade it to show the overlap, but I wasn't able to do it using the program I'm using. So this will be sufficient for what we need. But to tell what our final answer is, I would look at the ones that are shaded this way and this way, because it's a fraction of a fraction. So this is one fraction, and then the other fraction is going this way. So the ones that are taken up by both, those would be the ones that we're looking at for our final answer. So in this case, it's 4/10 or 2/5. Bar modeling. So this is one of my personal favorites. It's similar to the other one. So here we've divided our bar here into fifths, and I've left 4 of them unshaded. So in this case, 4/5 of the bar is unshaded. And then down here, half of each fifth from the 4/5 is now shaded as well. So what's left over? There's only 4/10 that is left unshaded. And again, that's the response we get, which is the same thing as 2/5. So fraction circles or the pizza model are also great. So in this case, again, I have 2 halves of a pizza, and 4 out of the 5 pieces from each half, or from this side of the half, I should say, have a giant pepperoni on it, which is representing 4/5 of 1/2. So when we go back and look at our total pizza, we see that it's 4/10 that we're talking about. So again, this is just a way of representing that same equation we've been looking at, but this time using fraction circles. So a number line model works really well as well. In this case, you take one of your fractions to be your whole, and then you divide it by what the other fraction is sort of saying. So in this case, I sort of flip the expression, which I'm allowed to do. When we multiply, we can change the order of the 2 numbers that we're multiplying, and it still produces the same product. So in this case, I took 4/5 to be my whole, and then I took half of the 4/5, which visually we can see is 2/5. So this one's kind of cool because I can skip the reducing of 4/10 to 2/5 that we would do if we were just using our abstract or our algorithm. Okay, using counters. So counters is another way that we can represent operations of fractions. Sometimes we kind of forget about them because they seem a little bit on the simple side, but you would do the following. So you'd start off by representing the first fraction. So in this case, it's 1/2. So I've done that by having a black counter and a white counter. And then I've done 5 rows of that, which is shown here. So I have 5 rows of halves, which is sort of taking care of the denominator. And then I'm taking only 4 shaded ones from that denominator of 5. And so that's equal to 4/10, or again, can be reduced to 2/5. Okay, on to our division representations. So the first one is the area model. So similar to multiplication, but in this case, when we talk division, we're talking about how many of one fraction fit into another fraction. So in this case, it's pretty easy to see that 2/4 fit evenly into half of this shape. We could also use our least common denominator to help us out with this. So we have a new expression here. We have 1/2 divided by 1/8. And so if we change the first fraction to 4/8, again, we divide up our shape appropriately. And then we say how many single eighths are in there. Well, there are 4. And this is helpful too when you have sort of more complicated fractions. 1/2 and 1/8, they're sort of friendly. They're sort of in the same family. But if you have different fractions that don't relate as well to each other, then this can be helpful finding a common denominator. We can also use fraction circles. So we kind of take 3 steps to do this. So first, you're going to take one fraction circle and you're going to represent the first fraction. In this case, it's a half. So again, I can't shade it in this program, so I've just put a giant circle there to represent that. You're going to take your second fraction and you're going to represent that. Also note in this example, the second fraction is larger than the first fraction. And in C, we now figure out what fraction of the second fraction. So how much of the 3/4 will fit into the first fraction, 1/2? So we have 2/3 of the 3/4 that fit into 1/2. So we see it visually here. The overlap are those 2/4. So 2/4 of 3 fit into the half. And that's what this fraction here represents. It basically represents how many quarters fit into a half. So we can also use bar modeling. So in this case, I've taken a bar and I've shaded in 1/4 of it. I'm going to do one below. I'm going to divide that one into thirds, which is the second fraction. And in this case, again, I used a common denominator. So I figured out that a great common denominator to use would be 12. And so I can divide each of my fourths into 3 and each of my thirds into 4, and then shade in the appropriate number here. And when comparing the quarters to the thirds, 3/4 of a third fit into a quarter. Okay, so now number line model. This one's interesting because it actually reflects the invert and multiply, or taking the reciprocal. So we have a different expression, 2/3 divided by 1/4. And we know that when we invert and multiply, or we take the reciprocal and multiply, you flip the second fraction, so it becomes 4/1, and then we multiply. So in this case, I've already reduced it here, but you would end up with 8/3, which can then become 2 2/3. So in representing that here, I have 1, 2, 3, 4, 5 along the bottom, and then I've divided the line in between the whole numbers into thirds, and I'm skipping by 2/3 at a time. And I've done that 4 times, and that brings me to 2 and 1 2/3, 2 and 2/3. Okay, I'm just going to quickly discuss why taking the reciprocal works. And this is sort of advanced. It's kind of like a grade 9 concept. But I'm going to set up our, just a standard dividing fractions question in an algebraic form. So we have x, which is a number that we don't know, and we have 3/5 divided by 1/2 is going to give us x. And we're going to do some things to rearrange this expression to show why we can do the taking the reciprocal method. So I can actually rearrange the equation. I can bring 1/2 over to the other side of the equal sign. And originally here, it's divided by 1/2. When I bring it over, I have to change that sign to multiply. So whenever you have a variable beside another number, it automatically means that you're multiplying. So in order to keep the quality, I have to change it to multiply. And maybe in another video, I can show why that works. If you do a simple expression, 2 times 2 equals 4, and then you move the second 2 to the other side, you can say 2 equals 4 divided by 2. So by moving the number and flipping the sign to sort of its complementary sign, the number or the expression stays true. So from there, what we can actually do, we can cancel out this half by multiplying that whole side by 2. However, if we do that, we have to do the same thing to this side. Again, that's another way that we maintain equality, right? If we add the same thing to each side, it still equals the same thing. And again, you can try that with simple numbers to see if it maintains equality, but you'll find out that it does. So because that cancels out, we end up with 2 times 3/5 equals x, or 2/1, which is the same thing as 2, which gives us 6/5. So yeah, that's why the taking the reciprocal method works. A lot of the times we're taught kind of these tricks or these shortcuts, which are really great, but it's important to understand the concepts behind them so that we're not just kind of using math wizardry to get by, but we're using our understanding of math as well. All right, I hope that helps and gives you a bunch of different ways to represent multiplying and dividing fractions, and hopefully it helped clear up some misconceptions around what might be improper ways of representing fractions. So thank you so much for watching, and I'll see you next time.